Class number 13, the last one. Sound when in motion. If there's motion of the sound source and/or the listener, the frequency of the sound that is heard may be different than the one being produced. Here's a typical example. It's called the Doppler Effect. Here's the explanation of why it happens. A stationary source generates equally spaced wavefronts in all directions. But if it moves, wavefronts are generated closer to each other in the direction of the motion and more spaced in the opposite one. But this cannot be news for someone studying physics or engineering. This is high school stuff.
Must have missed that day at school.
However, the first statement was not so high school. Why may? Is there a case when it does not happen?
When the listener and the source are both moving in the same direction and at the same speed.
That's correct. Can you think of another one?
Nope.
Back in the 60s, this was this very popular hobby known as U-control. Though old tech for today's standards, some still enjoy the thrill of it. The model plane flies in circles around the U-controller. Can you hear the Doppler effect? Everyone watching the flight could hear the Doppler effect, all except the controller. Here, though there is relative motion, the distance from the plane to the controller is always the same. What counts for the Doppler effect is the relative distance rate of change. It was Christian Doppler who first suggested the effect. Not for sound, though, since nothing moved that fast back in 1842. But as an explanation to the color of binary stars, in which the one moving towards us looks bluish, while the one moving away looks reddish. A little math?
Oh, here we go again.
Crybaby. Consider a reference frame in which the propagation medium is at rest. Now, there's a wave source moving toward an observer with a velocity v sub s. Also, the observer is moving toward the wave source with v sub o. The wavelength lambda equals the product of the wave velocity relative to the source by its period, which is the inverse of the frequency. Are you with me? Good. For the observer, the time t between crests would be the quotient of the wavelength lambda over its relative speed to the wave velocity, or its frequency, replacing lambda here, and we get to these equations that we're going to frame. That is because this is the equation for the Doppler effect. However, it was not Doppler but Hippolyte Fizeau who came up with the equation in 1848. In vector form, the equation looks as follows, where r is the unit vector that points from the source to the observer. Only the motion that contributes to the change in the distance count for the Doppler effect. And I'm going to frame this assertion as well. Let's put this knowledge to good use. Here's an ultrasound scan of the side of your neck, showing the internal jugular vein, IJV, and the carotid artery, the one with CA. Blood flow carries red and white cells. That produces some Rayleigh scattering of the ultrasound beam. The scatter wave comes from moving cells. Some, say in the artery, move toward the transducer, while those in the vein move away from it. Scattering from the artery will show a positive Doppler shift. A scattering from the vein will show a negative Doppler shift. A color Doppler machine will assign red whenever it detects a positive frequency shift, and blue if negative. Can we estimate how much would that Doppler shift be for 5 MHz?
For that, we would need the velocity of the blood cells, but we don't know that, do we?
Could you figure it out if I told you that the flow through the carotid is an average of 400 milliliters per minute and that its average diameter is 6 millimeters?
Between 23 and 24 centimeters per second.
That's correct.
God, the end is near.
Say we take 24 centimeters per second as the blood cell velocity. But is that the distance rate of change? No. The transducer has an angle alpha with a flow of about 45 degrees. So those 24 centimeters per second must be multiplied by the cosine of 45 degrees, which is about 0.7. The distance changes only about 17 centimeters per second. Are we ready to do the estimate using the Doppler Effect equation?
Oh, we are.
Speak for yourself.
Okay, who's the observer and what is the sound source in this case?
Yes, that's what puzzles me.
The thing is that there are two moments to what happens here. First, the transducer emits a short ultrasonic pulse that hits the blood cell. The transducer is a fixed source, and the blood cell, the observer that's moving toward it at 17 centimeters per second. The speed of sound in blood is about 1600 meters per second, so the frequency that the blood cell experiences is... Replacing symbols with values and not forgetting to convert centimeters to meters before calculating, the result we get is the original 5 MHz with a small shift of 531 Hz. The second moment, the cell vibrates as a Huygens second source. It is a moving source with a shifted frequency. Here's the Doppler equation again. Now we replace the symbols with their values and we calculate. The Doppler shift from the scattering of the carotid is then plus 1063 Hz. While that from the scattering of the jugular is the same but negative, minus 1063 Hz. A color Doppler ultrasound machine will assign red to those echoes with a plus shift and blue to the ones with a minus shift.
And you want me to believe that such a machine detects 1000 Hertz in 5 million? Come on.
I will just say this, a UHF walkie-talkie channel is 1.5 kilohertz wide. If it misses just 1 kilohertz, not in 5, but in hundreds of megahertz, it is already talking in somebody else's channel. Accuracies in radio frequencies are expressed in ppm, which stands for parts per million. Here's something for the non-believers. The radar gun. But first we want to derive an easier expression for the Doppler shifts. In almost every case, the velocities of the observer and the source are much smaller than the wave velocity. Here's the Doppler effect equation after dividing above and under by the wave velocity. Being the denominator so near to 1, this is a very good approximation. Now that the quotient has turned into a product, let's do the product. A very small number squared is a very, very small number that can be neglected. The relative shift then results in this expression. In the case of the radar gun, the same as in the ultrasound Doppler, the V sub O equals V sub S. And so the expression for the relative frequency shift reduces to twice the ratio of the speeds. And what's the slowest speed limit you can think of?
A school zone in the US may limit the speed down to 15 miles per hour.
Yes, that will be a good minimum enforceable speed. That's about 25 kilometers per hour. So the minimum relative shift the radar gun should sense is 4.6 by 10 to minus 8. Knowing that these radar guns operate in the microwave K band at 24.15 gigahertz, the shift in hertz would be 111 hertz.
111 and 24 billionth with a B. Give me a break.
Give me a minute and I will tell you how it's done. The radar gun beats the signal it transmits with the echoes it receives, resulting in something like that. Each beat accounts for 0.227 kilometers per hour per beat, or 0.141 miles per hour per beat. So counting the beats, you can tell the speed. I know what you're thinking. The answer is yes. It works under the same principle.
For it's 1, 2, 3, stretch her out at the old morning.
But here's the ultimate. In the radar gun, we dealt with a relative Doppler shift of 4.6 by 10 to minus 8, right? Well, there's something called the Mossbauer spectroscopy, in which relative shifts are in the order of 10 to minus 12. In case you don't realize what this figure implicates.
Of course we do, don't we?
We're talking about an effect that is sensitive to observer and or source velocities that are 10 to minus 12 the speed of light. Being the speed of light 3 by 10 to 10 centimeters per second, the velocities involved in this Mossbauer thing is in the order of 10 to minus 2 centimeters per second. In other words, millimeters per minute. Nothing yet? That is slower than the minute arm in a grandfather. A gamma photon is born upon the down transition between two energy levels in a nucleus. For such a gamma photon to be absorbed by an identical nucleus, its energy must be accurate down to 10 to minus 12. The mere energy loss due to the atom's recoil will prevent it from happening. The energy loss from recoil is 1.34 by 10 to minus 7 of the gamma photon. That would be 7 times the recoil energy of an aircraft carrier if a sailor jumped from its deck. If the atom belongs to a crystal lattice, then the recoil will be much less. For all it can do is vibrate and generate the sort of sound wave we know as a phonon. Recoil is now so small that absorption by an identical nucleus may happen, but still with a small probability. What if it gets a little help from its friends? The help it needs is little indeed. The Doppler shift, or just moving the source a few millimeters per minute, will allow the sample to absorb more of the emitted photons.
Okay, awesome effect. But what's the spectroscopy you mentioned?
Chemistry not only affects the electron cloud, but somewhat the nucleus energy levels as well. Magnetic fields can also split the absorption peaks, and this resulting in a complex spectra, hence spectroscopy. Now we move from speeds that are much smaller than that of the wave to those that are near or even beyond the propagation speed. Here's when the source is still below the propagation speed. But you're familiar with this, right? Here's when moving at a propagation speed. Boom. Boom. And boom. Here's when moving beyond the propagation speed. The sonic boom is heard after the source is already past the listener and moving away from it. There you go, boom. And boom. This is quite a picture of a jet fighter going supersonic. There's high pressure at the edge of the cone. This rarefies and cools the air behind, causing moisture to condensate into a noticeable cloud that reveals its shape. Can we estimate the speed of this fighter plane? The angle of the cone is 63 degrees. You can trust me, I measured it. Let's pick a wavefront. And this is how much the jet has moved in delta t at a velocity v sub s. It is straightforward that the sine of 63 degrees equals the ratio of the speed of sound to the speed of the fighter. So we did it. That jet fighter is doing 1.12 Mach, which means 1.12 the speed of sound. There's no need for a jet plane. Waves in a pond propagate slow enough for the ducks to do a wake boom.
And now the light boom, right? There's no such thing, you idiot. Since the special theory of relativity back in 1905, it is known that no matter can move faster than light.
I see that you're an expert in this thorny subject of special relativity. Then maybe you can explain what is the TDE, or transverse Doppler effect. This is not a class in special relativity, but it's good to know it exists. It happens that with light sources moving at relativistic speeds, when seen at its minimum distance, a shift to the red is observed, even though this distance is not changing. Also, remember the U-control model plane in which the controller didn't hear the Doppler effect? Well, a Mossbauer experiment in which the absorber was spun around the radioactive source registered a blue shift. In both cases, the relativistic dilation of time was responsible for the observed frequency shifts. And this is called TDE, or transverse Doppler effect. But it's already that time. Time for the quiz. Here the answers will follow the question or problem, but hit pause and try answering it first. Problem number 1. Formula 1 race cars are speeding by at 230 miles an hour on a racetrack that is 100 feet away from an observer. In case you need to know, the speed of sound is 767 miles an hour, and 1 mile has 5,280 feet. Question A. What is the maximum total relative Doppler shift that can be heard? B. How far is the car at the time when no Doppler shift is heard? And C. What is the frequency ratio when a car is at its nearest distance? In your calculations, keep your accuracy below 1%. Hit pause and try to answer question A. Question A. What is the maximum total relative Doppler shift that can be heard? The maximum positive shift happens when approaching from very far away. The maximum negative shift is when far and distancing. We had this very simple formula that made it very easy to calculate relative shifts. Since the observer is not moving, V sub O is 0. simplifying it further to this. And so for the negative shift, bringing the maximum total relative shift to this. But is this under 1% accurate as requested? This approximation was valid only when the velocity of sound was much greater than that of the observer. But is 767 much greater than 230? No, it is not. So we must go back to the original Doppler equation. The maximum total relative shift is then 0.66 plus minus 1%. Let's take question B now. B. How far is the car at the time when no Doppler shift is heard? When the car is nearest to the observer, there's no Doppler shift, because there the distance rate of change is 0. That unshifted sound wave arrives at the listener at a time delta t, which equals the 100 feet divided by the speed of sound. During that time, the car has moved v sub car by delta t. Now we do Pythagoras and we have the requested distance d, which comes out as 104 feet plus minus 1%. And see, what is the frequency ratio when a car is at its nearest distance? When the car is nearest to the observer, the sound that is heard was generated sometime delta t ago when the car was at point v sub car by delta t to the left. The distance to the set point equals the velocity of sound by the same delta t. For the Doppler equation, what we need is the distance rate of change, which is not the speed of the car, but only its projection in the direction of the listener, or v sub car by the cosine of alpha, that angle there. From the figure, the cosine is straightforward. And of course the delta t is cancelled. Replacing v sub s in the Doppler equation, dividing up and down by the speed of sound, replacing the cosine by the speeds ratio. Evaluating, the requested frequency ratio is 1.10 plus minus 1%. Notice that it doesn't depend on the distance to the observer. Problem number 2. The example of the carotid ultrasound examination using 5 MHz rendered an average Doppler shift around 1 kHz, which is an audio frequency in the most sensitive hearing range. Continuous wave ultrasound fluximeters outputs audio that allows hearing the Doppler shifts. Listen to the carotid and watch its spectrum. Here 4 MHz is being used, and the transducer is at 45 degrees with the artery. Estimate the speed of the blood cells echoing the highest peak. For the speed of sound in blood, you may use 1600 meters per second. And question B. Fluximeter used 2 MHz for the heart, 4 MHz for the carotids, and 8 MHz for the hands and feet. Why? Hit pause. Okay, let's answer question A and estimate the speed of the blood cells echoing the highest peak. From the radar gun, we'll learn that for velocities much lower than the wave, the Doppler shift was twice the distance rate over the wave speed. The distance rate is not the velocity of the blood cells, but only its component in the direction of the receiver. Replacing the cosine of 45 degrees with 1 over square root of 2. Now we isolate the velocity of the sources v sub s. It's time to replace the symbols with its values. The speed of sound is 1600 meters per second. The ultrasound frequency of 4 MHz is 4000 kHz. And from the spectrum chart we can estimate the Doppler shift as 2.52 kHz plus minus 1%. And after putting the calculator to work, The speed of the blood cells is 71 centimeters per second, plus minus 1%. Question B. Here's the answer for the frequency going 2, 4, and 8 megahertz. Doppler shifts are proportional to the ultrasound frequency. Blood cells' velocities are greater near the heart, somewhat less through the neck, and finally slower at the extremities. The best choice of ultrasound frequency is the one that renders the Doppler shift in the low kilohertz audio range. Problem number 3. In the Mossbauer spectrum shown, the gamma radiation used is 14.4 kiloelectron volts, and the sample is under a magnetic field that has split the energy levels, creating two absorption peaks. Estimate the energy separation between the absorption peaks. For solving this problem, we can use the approximate expression for the Doppler shift that in this Mossbauer scenarios become almost exact. Now we multiply above and below by the Planck's constant and we get the energy ratio. We can then isolate the energy shift. From the chart we can estimate the velocities at which the absorption peaks happened. Replacing the symbols with their values and the positive velocity of the highest energy peak we get. Doing the same for the peak with the lowest energy. Finally, we add both shifts and we get to the result, which is 1.39 by 10 to minus 7 electron volts. Notice that the relative errors we admitted when estimating the velocities from the chart must be added for the final result, which is 1.39 by 10 to minus 10 electron volts plus minus 20%. Problem number 4. Say that a supersonic jet flies very near our observer at 1.2 Mach. Part A. Estimate the frequency ratio of the sound produced after the boom. Part B. Estimate the frequency ratio of the sound produced before the boom, but that reaches the observer after the boom. Part C. The frequency ratio in Part B was negative, right? Explain the meaning. Part D. Estimate the frequency ratio in Part B, but for Mach 2. Hit pause. Let's start with Part A, that of estimating the frequency ratio of the sound produced after the boom. What we have after the boom is a static observer, that is V sub O equals 0, and a source distancing at very approximately 1.2 Mach. Here's the Doppler equation. So the source is moving away at V sub S equal minus 1.2 the velocity of sound. We'll replace the symbols with the data, and the calculation renders a frequency ratio of 0.42 plus minus 1%. Let's do Part B now, so we have to estimate the frequency ratio of the sound produced before the boom, but that reaches the observer after the boom. During the time that the source was producing the sound before the boom, it was moving toward the observer, so V sub S equals plus 1.2 by the velocity of sound. Change the sign of the source velocity in the expression for the frequency ratio. We now get minus 5. The frequency ratio is negative and 5 times the original frequency. Very high-pitched. Part C requests explaining what's the meaning of that negative sign. Well, it happens that the sound produced the last arrives first. The minus sign means that the sound is reversed. Say the sound was 1, 2, 3. What you would hear is. Part D requests estimating the frequency ratio in B, but for mesh 2. Calculating the frequency ratio for V sub s equals twice the velocity of sound, we get -1. This means that though the sound's still reversed, the frequency is the same. At higher speeds, all the pitches are lower. And problem number 5 is a question. Why, if all these jets can make better than mesh 2, the cones revealed by the boom clouds are always so wide? It pause, and my answer is, the wave packing happens only near mesh 1, when the aircraft just breaks the sound barrier. At no other speeds, the air compressions and rarefications are large enough to create boom clouds. This course in the physics of sound has consisted of 13 half-an-hour classes. They started with a timid advice in the use of some terms, just to avoid sounding too ignorant, and ended up with a supersonic boom. It has gone through oscillations, the free-running and then the ones that are forced, where the concept of resonance was introduced. This was followed by waves, traveling and then standing, which led to the physics of music. Scales, temperament, consonance, dissonance, and the human ear's magic. It could have ended there with a high note. But then it would have left out the reflection, refraction, diffraction, and interference, as well as their imperfect cousins, the diffuse reflection and wave scattering, which led to the collocation and its medical refinement, the ultrasound imaging. It could not leave out that of waves in periodic structures that went from the Mayan singing pyramids to the phonons in a crystal lattice. Those who have gone through the 6.5 hours of video may have certainly come nearer to their master's degree in physics. If that's the goal, subscribe to the channel.